So welcome everybody. Today with us, we have Martina Teruzzi. Martina is a postdoc in the CISA MATLAB group. And today she will talk about digital twins and graph theory, a parallel thought simulation software with naval application. Thank you, Martina.
Thank you, Maria. Thank you for the invitation. Actually, as Maria was saying, I will talk a bit about what I think is the connection between digital twins and graph theory. And the first thing I would like to do is I would like to mention that this work has been done in collaboration with Nicola Demo, Marco Tezzele, and Professor Gianluigi Rozza at MATLAB, CISA. So, okay, let's start from the beginning. If you look at Wikipedia, which is always the first thing to do, you would see that digital twin is defined as a virtual representation of a physical object or process. Now, this is pretty general as a definition, but I hope that the image that you see would be more evocative. So imagine to have a twin, but this time to have a particular twin, a twin which is digital. Now, in order for it to be a twin, you would like it to have all your parts, all your components in a sense, but also to behave as you behave. In this way, it can be actually recognized as a twin. I mean, how do I see as twins? Actually, if you look at industrial applications of engineering design, a digital twin is the climax of a long, very, very long period of simulations and modeling in industry, which started a lot of time ago, before the 80s. Now, a lot of revolutions happened and a lot of new things came. Lastly, the data, but also a lot of other things. So we are finally in this digital twin era. That's what they call it. Okay, but how do we define the digital twin then? I would like to give some description, some definitions that are good to me and to what I will present later. So first of all, a digital twin is a linked collection of data. These data are engineering data. As I said before, they are not just descriptional data in a sense, how to know that a twin is a twin because you have the same shape, but also the same behavior. So you also need operational data from industrial processes in such that you have a good behavior description of your process. Secondly, the simulation you make on the digital twin should be of use for the real asset, meaning for the physical object. So they have to be of some suitable fidelity for your problem to be solved. They cannot be any kind of simulation. Now, what is a suitable fidelity is definitely a relative thing, and you may define that depending on which is the application. Third, this is really important thing, your real system will evolve in the design phase, but also after that. So you would like your twin to accompany the object for the whole life cycle. And to integrate it, so anytime you get new knowledge, you get something new from your real asset, you should integrate that into the digital twin. So ideally, the twin is evolving together with the object itself. For a digital twin to be useful, a digital twin is useful if it provides any solution which is good for the real system. And of course, in this sense, the simulation models have to be specific. We go back to the second point. And lastly, we could say that the optimization, normally is done in the design phase, but it should be continued in the operation and maintenance phase. This is pretty important, especially if we have a real asset which is not available, not of easy inspection. Because the digital twin is something we model, is something we have with us, and it's pretty much easier to inspect the digital twin if it is properly created than the object itself. Okay, now I'm just giving you one last definition in a sense, because I would like to give you an idea of how diverse is the zoo of digital twins that you could find around. Now, this is a definition of how the physical object is connected to the digital object. And you can define a digital model, a digital shadow, or a digital twin, depending on how much automatic is the data flow from the physical object to the digital object. If it is fully manual, then you have a digital model. If it is fully automatic, you have a digital twin, and you have a digital shadow in between. Why I'm giving you this description of the level of integration of the digital twin with the real object, because actually, even though a definition exists, you would probably find out in a lot of articles or, a lot of sources, you will find out that everything is called the digital twin. So, there is a lot of generality, but you have to be a bit careful about the definition. Okay, now that's all very nice in general, but how do you represent a digital twin? Today, I'm going to give you an example on how we do that, and especially in the field of industrial plans and of risk analysis. Now, I'm going to present you a software, which is called GRAPE, Graph Parallel Environment. It is based on graph theory, and it is able to model complex interconnected systems like industrial plants. What does it do on these graphs? It performs risk analysis, and after the risk analysis, it performs a complete fault system diagnosis of the system. Important thing to say, this is an open source software, so if you want to play with it, I really welcome you to do that. You can just go on the GitHub page and, try to play with it, ask questions if you have any, so it's really free. Okay, what is GRAPE? GRAPE is a Python free package. It is based on a previous work by Aurora Maurizio, a former MATLAB member, and it concerns of 3 main steps. Now, the first step is the graph characterization. Graph characterization means that you give a list of components, of nodes, you have connection between them, which are the edges, and on the graph itself, you can already do a lot of things, kind of calculating the shortest path, calculating some measures, which are typical of graphs, centralities, efficiencies, and also service, which is an additional one I will talk later on about. Now, graph characterization, the part of graph characterization can be seen as a standalone. So ideally, you could use just the part of the graph. Now, the reason why I say integer graph characterization is, of course, because we would like to break this graph at some point and to simulate a failure on that. We have 2 different ways of doing so, which is element or area perturbation. The details are going to follow later. And whenever we perturb the system, we then optimize the switches configuration and we propagate the damage in the graph with a cascade effect. So going from one node to the neighboring node and so on. After the simulation of the failure, then we give a characterization of the damage graph, again with the calculation of shortest path and of all the other measures that allow us to describe the graph in a, I would say, really precise way. Okay, so we want it to be as much quantitative as possible in this, in our, description. So we chose weighted graphs. Weighted graphs actually happen to be a very efficient solution. I told you that we would like to use graphs to model industrial plants. So the main idea is that you have some commodities that flow in these plants, and weighted graph is a really efficient solution to specify the best itineraries for the graph, the best path that you would like to run with respect to other paths and other areas which are less favored for some reason that you may have. This concept is of immediate integration, of course, with a description of the network with the graphs, and you can compute the shortest path. And as far as you have, let's say, depicted your weights in the right way, then the shortest paths are also going to be the best one to run. We have 2 different ways of computing shortest path, 2 different algorithms, depending on the density of the graph itself. So if the graph is sparse, then you have Dijkstra's algorithm. Otherwise, you have Floyd-Warshall algorithm. Let's start from the sparse graphs. Dijkstra's algorithm starts with all the nodes in the graph set as unvisited and all the distance between pairs of nodes set to infinity. You start from one node and you visit all the unvisited neighbors of the node. The node that you are visiting currently is defined as current, and you go on visiting all its neighbors. Now, you have one vertex, which is the starting part of your shortest path, and you try to compute the distance from this node to the unvisited neighbors through the current node, passing through that node. If this distance is smaller than the one you had in memory, then you update it. Otherwise, you don't. Now, the first time you do so, you will have infinite for all the distances. So that's pretty, obvious that you're going to update it. And then you're always going to compare with what you have back. And if you get a smaller distance, then you update the path. Very important is to say that when all the neighbors of your node have been visited, the current node is marked as visited, and it's never checked again. This means that for every node, you have one shot, so you cannot go back. Now, Dijkstra's algorithm is an algorithm of order E plus n log n. Now, E is the total number of edges in the node, n is the total number of nodes. And if you want a null pair distance, so computing all the possible distances from, with all the possible pairs of nodes, let's say, you have to multiply again times n to get the total cost. For dense graphs, Dijkstra's algorithm is not the best one. Floyd-Warshall is the one. And actually, differently from Dijkstra, Floyd-Warshall algorithm computes all the possible routes between two vertices I and j. So you have two vertices, I and j, the head of and the tail of the path, and you try with all the possible other nodes different from I and j, try to pass through them. If the distance you get is smaller, you update the distance and the predecessor matrix. Otherwise, you do nothing. Now, once you have your final distances matrix and predecessors matrix, you can reconstruct your path and having the shortest path. This algorithm is of order n to the third, again, where n is the total number of nodes, so it costs more in terms of nodes, again, for all pair distances. Okay, now, once you have the shortest path, you can compute actually a lot of measures on that. The first one you can think about is efficiency. Efficiency is the inverse of the path length. If the path has non-zero length, let's say, and it tells you how quick it's to go from one node to the other. This is a really, I would say local measure in the sense that every path has its own, but then you would like to compute some other averages, for example. And nodal efficiency is really a close friend of the efficiency, just it is an average on, for a fixed, let's say, starting point of the path, you can have an average for all the outcoming paths. Local efficiency is another. Global efficiency, for example, is just a number. It gives you the average total efficiency of the pairs of nodes. You have also centralities. I'm not going into the details of all of them. In any case, for example, centralities, are more about how connected is the node. So how many edges it has. For example, the betweenness centrality is proportional to the number of shortest paths that run through the node. Now, it may seem, let's say, just a measure, but you always have to think about that then we are going to apply this algorithm on plans, and what we would like to do, would like to break this plan. So the more a node is central, the more if you remove it, you're gonna create problems. So, these measures have some meaning for us in this sense. You have a lot of them. In degree centrality and out degree centrality, for example, are giving you an idea of how many paths, outgoing paths and ingoing paths you have for one node. So, you have a lot of them. Okay, now, I'm not going to go into the details of the code. You can find it on the GitHub page, but I just wanted to mention that for the shortest path calculation and for the graph measures, we always have a parallel version of them. We used Python multiprocessing, and here in the graphs, you can see the results we got on synthetic data. On the left, you have the Dijkstra's algorithm for sparse graphs with sizes from 1,000 to 10,000, while on the left, you have the Floyd-Warshall, so dense graphs, with sizes from 200 to 1,000. And what I'm plotting is the speed up. Now, speed up is how much you gain in terms of speed with respect to the serial calculation. And we have different numbers for different sizes and different algorithms, but you can see that we can arrive to 20 times the speed that we have for the serial case. This may not be a problem, I mean, speed for a really small graph, but if you think about applying that to large graphs, for example, to large plans, and if you think about the fact that you are doing risk analysis on these plans, you're going to understand that efficiency is a matter, and being more efficient is definitely a plus. So that's why I wanted to say this. Okay, now, what is a graph? A typical graph for a grape. It is a really simple graph. Actually, it is the graph we use for testing. But even though it is so simple, I think it contains all the elements that you need to understand to be able to understand grape. So we have 3 different types of nodes. We have sources, I color them in blue. We have hubs, which are black. And the only user that we have here is 18, which is red. Then you have particular types of node. We're going to see why, which are switches. And here 2 and 3 are switches. And this halo around node is going to tell you that these nodes are perturbation resistant. And now this graph is divided into 4 areas. Areas are a matter of, I would say, commodity in the sense that you can treat the nodes that are in the same place, propagating the damage all together in one area. So that's also one of the reasons why we divided them. And last but not least, the edges. So the edges are fundamental because they tell you how, I mean, what are the logic relationships between the node and how everything propagates in the graph. Now you can have or, and single edges. I mean, you always call a father a node which has an incoming edge from it to you. Now, if you have just or fathers, at least one of them has to survive for you to stay alive. If you have all and fathers, all of them have to survive in order for you to stay alive. And if you have a single father, then, I mean, it doesn't matter if it's or and. If the father dies, then you're gonna probably be broken. Okay, now, what are all these names? Actually, I mentioned before a lot of measures, but I left out one, which is service, and it's pretty important for us. It is a quantitative description of the system residual capacity. I told you that we are using graphs to model industrial plants, and service just tells us how much of the, let's say, how good is the flow and how much we get in the end of all the service that is provided by sources. The nodes have been labeled depending on their role when service is taken into account. Sources are the one that provide service. Users are the one that deplete service. And hubs are more or less all the other nodes in a sense that they are the one that belong to the shortest path, which are neither sources nor users. And if you think about a plant, you understand why we need this source-user relationship. Before in the toy graph, we had just one user because it's pretty, I mean, it's really a toy graph, but for each source, its service has to be split between all the surviving users which are connected to it. Now, sources and users may seem just a label, but ideally, if you think you want to connect, for example, plants, you may think that the sources and the users are somehow the inputs and the outputs in terms of commodities of your graph. And you can exchange in some way information on which is the state of the system, saying how much service you have left. And of course, maybe your output may go as an input to another plant. So this is the way we model it. Okay, as I said, a particular type of hub components is a switch. We're going to see how they work later, but just to give you an idea, they are an active resistance to faults and then can be turned on and off during the perturbation to block it, to avoid a complete break of the graph. How do you perturb a graph? You have 2 possibilities. One is the element perturbation, meaning that you can specify one node or more nodes to be broken. And area perturbation, again, you can specify one or more areas to be broken. What is important to understand here is that starting from a node, the damage propagates in all directions. So it can go to neighboring nodes, but it can go also to neighboring areas, arriving to break all the nodes if it is not stopped, of course. How can we stop it? We have two principal ways of perturbations resistances. Now, the passive resistance is that halo that I was describing before around the node. And it's our way to say that that node is resistance to the perturbation. What I mean, there is always a passive resistance. If you think about, I don't know, fire can propagate in a plant, and you always have some elements that are fireproof. Fireproof cables, fireproof elements. So in that case, you don't have to do anything to activate the resistance, and that's the way we describe it. But it is also really funny, the active resistance, in my opinion, because those are nodes that you have to activate to avoid the damage to go to neighboring nodes, and those are the switches. Okay, let's give you an idea on how the switches work. This is our beloved toy graph. And on the top node, imagine that the top node gets broken. It is involved in a perturbation. And as far as we do not limit the damage is going to propagate to the neighboring nodes, probably arriving to the whole graph because it is all connected. And the situation on the left is what we do not want. What we would like to have is the situation on the right. The two most close nodes to the top are switches, and we would like to open the circuit and avoid the propagation of the damage. We can do so. We can activate those switches, and in this way, just the top node gets broken and the rest of the graph is safe. This situation is pretty easy. Even by eye, probably, you could say which is the best thing to do. I mean, I could have said to you, just break one switch, and you would have said to me, no, the best configuration is to break the two of them. This is easy for now, but can you imagine what would happen with a lot of switches and with a really complex graph? You cannot do that by eye. So how do you determine in general which is the best configuration for the switches? The way that we do so is to use genetic algorithms. Now, a genetic algorithm generates a population of individuals with random genes and make them evolve mimicking Darwin's theory of evolution. It has three main steps. The first one is selection. The best individuals of the previous generations are selected in order to breed the new generation according to their fitnesses. And then we have crossover or mating. You take pairs of individuals, you make them mate depending on some random, on some defined probability. You exchange their genes, let's say, to create a new offspring, or more than one, depending on what you need. Mutation is another possibility to create a new individual, because individual can exchange their genes, again, according to some probability, creating a new individual. This can go for the good or for the bad. It really depends. And you compute the fitness and understand what's the situation. You iterate this process for some steps, which are called generations. And finally, you have all the generations and you keep the best individual of all the generations. We have not done genetic algorithms from scratch. Actually, we have used a pretty useful tool, which is DEEP, Distributed Evolutionary Algorithms in Python. And it is really nice because it allows you to play with a lot of data types, having the same structure for the genetic algorithms. And it contains a lot of built-in evolutionary functions, which I think, are really useful. So it is really nice to play with that. Okay, now what's an individual for us? What's fitness for us? This is still to be clarified. For us, an individual is just a set of states for the switches. So imagine that we have 10 switches. They may be true or false. By true, I mean, at least for us, true means that the circuit is closed. So the flow can happen, the service can propagate, but also the damage. So this is a closed circuit. If you turn it to false, the circuit is open and the damage gets blocked. So how do we define our fitness? What's the best state? We could have used a lot of different quantities. We focused on three. The first one is the number of actions. So imagine that I have two best states, two equivalent states. Again, I'm doing risk analysis on this graph. So I would like to go from the initial conditions, which is given in input for the switches, to the final condition with the less number of actions possible, the less flips let's say, of the switches. Maximizing, definitely another quantity, which is the total final service at the users, and maximizing the total number of surviving nodes. I mean, these nodes are modeling plants and components. So ideally, I would like the graph to be as complete as possible, with, of course, definitely a good service. Now, okay, so we minimize the first quantity, as you can imagine, and we maximize the other two. Okay, now that you have understood everything about grape, let's try to simulate it. Okay, on the left, pardon, you have the toy graph, which is the integer for now. So you have two sources, 1 and 15, and source 1 as service 1 provides service 1, and source 15 provides service 2. Okay, now both of them are connected. They have a path with the only user here, which is 18. So no surprise in saying that the total service at the user 18 is 1 plus 2, which is 3. Okay, now imagine that you perturb node 1, as always, the one at the top. And imagine, I mean, you can have different possible configurations for 2 and 3 here, which are the switches. If you leave them through, meaning that everything can propagate, they will be also broken because the damage arrives also to them. And then the damage arrives to 4 and 5, which are perturbations resistant, passive ones. So the propagation stops. However, it is really easy to understand that the best configuration is for these two switches to be flipped so that they also remain alive. And the only node that is broken is 1. The total final service at 18 will be 2, of course, because node 1 got broken, so it is no more able to provide service. I mean, here what I wrote is just that, again, anytime we do some, let's say, breaking, some propagation, we compute, again, shortest path and measures because they give us an idea of what's the state of our graph. Okay, now I told you a lot about grape, but how do we use grape? This is a practical use implementation in the project SAFE, which we've been involved. I've been involved in my master in high performance computing. And SAFE is real-time damage manager and decision support. It's a Professor regional research project. It involves Cetena, SPA, Architect SRL, SISTA, Università degli Studi di Udine, and Lloyd's Register. The main aim of this project is to develop new tools and methodologies for the dynamic quantification of the damage that can occur on a passenger ship. And the main idea, the main goal, is to provide a decisional support tool for the crew. So the crew has to know which action it has to put in place in order to limit as much as possible the damage, to keep the ship safe and to maximize the residual operational capacity. Here you see, I mean, an example of a cruise ship together with its digital twin. That's what we have spoken up to now. If I would summarize my project in one phrase, I would probably say that the slogan would be, ship is your best lifeboat. So the main problems, the main failures that can happen in a passenger ships are normally due to fire and flooding. And again, I mean, if you don't limit the failure, then it's going to propagate all the neighboring nodes, neighboring areas in the ship, and it can ideally propagate to the whole ship. Casualty threshold is defined as the maximum amount of damage that a passenger ship is able to withstand, still continuing to sail. So the main idea is that abandoning the ship is really dangerous for the crew and for the passengers. So if you do not exceed the casualty threshold, you have a safe return to port scenario, meaning that, I mean, the damage has been limited, you stay on the ship, which again is your best boat, and you remain there going to the next safe port. Otherwise, if you exceed this damage, you abandon the ship. Now, 3 hours are normally given for abandonment. So this is just I mean, it's a pretty dangerous situation, which we would like to avoid. And the only way to do so is limiting the damage. Also, again, I mean, I've told you a lot about service, and service is the quantity we normally compare. I mean, not just that one, but with the casualty threshold. So you understand how much is important to be precise and to get the largest total residual service, now that you see how the casualty threshold works. What are we doing now? I mean, actually, we are in the design phase of our twin, and we are simulating on single plants for the moment, different kind of plants. But we would like, ideally, to combine everything on the overall ship structure. So to go to some larger structures or combined plants. In this sense, what I was saying before about parallelizations, about being efficient, the more you go, I mean, to a larger dimension, the more it is important. So everything has a sense, has a meaning now. Okay, let me conclude. I've presented GRAPE, which is a software able to describe complex interconnected systems like industrial plants. We have been able to model, I would say in a pretty general way, key concepts as the flow of commodities, practical ones, I mean, in such systems through weighted graphs. So through concepts that are inner of the graphs themselves. Service is fundamental, you have seen why. We can simulate the fault propagation in the system. We can mimic the cascade effect, but also we can automatically identify with GRAPE, which is the best configuration for the switches, to give a support for the crew, for example, in the case of safe. This software can be employed, is being employed in the development of a digital twin for fault analysis from the early stages. Future developments, actually current developments, I mean, I didn't mention it precisely here, but we still have to do the parallel version. I was speaking about parallelization of the evolutionary algorithm. That's the first thing we should do. And then we should definitely go testing our algorithm on more real test cases. We are having that from Cetena in our case. Finally, we are going to advance the best we can our digital twin. And we are continuously also speaking with partners, because our software is part of a pipeline. So this continuous interaction is, I hope, going to make advancement in our twin and make it the most suitable possible. Okay, so thank you for listening, and play with GRAPE. Visit us if you want. And I don't know, for any questions, I'm here. Thank you.
Thank you. Thank you very much, Martina, for this talk. Now it's question time. So if you have a question, as usual, you can unmute yourself and ask directly to Martina your question. So let's see if someone has questions. In any case, I have a lot of curiosities, Martina, so maybe I can start.
Yeah.
The first thing that I want to ask, I mean, it's my fault. I didn't understand actually in the first definitions that you gave us about the digital twin or the various digital twins. What do you mean about
a lot of them.
And automatic? In the sense, can you give me an example?
This one?
Yes, exactly.
Yeah. So ideally, I mean, you can have two different. I mean, it's actually more easy to say what I mean by manual. By manual, I really mean that the data have to be manually given to the digital object.
Okay.
The best thing, I mean, the best integration would be, I don't know, you can imagine a lot of digital twins, but imagine that you have sensors in one object. Ship can be one, but there are a lot of them. If you have your twin installed in the proper way, it can immediately, let's say, communicate with the twin itself, and this is, let's say, real time, and it can give you answers. If you have to do it manually, it becomes more like, I would say, an offline check. That's what I would call.
Okay, so manually, you are talking about a person that actually puts the data inside somehow.
Yeah.
Okay.
Yeah, as I told you, there is a zoo of them. I mean, when I read these articles about digital twins, actually, all of them are digital twins. I mean, I had really to find the definition. I really had to search for them. But yeah, I mean, the best digital twin would be, I mean, of course, that's not in the design phase. In the design phase, you are creating the software. But after that, you should be able to install that, and it should work with input data from the object itself. And imagine, I don't know, for example, for us, for a ship, that would be the best because you are in a moment of danger. So ideally, it should be able to, I mean, I don't know, your software should be able to be queried, asked from the person in the case, but already online on the ship, for example. That would be the best.
Okay.
Otherwise, you can do monitoring, but it's different.
Okay.
That's what I would say. Yeah.
Okay, I see. Thank you. And another question that I have is about the time that you need, you know, to do I don't know, a simulation like that, because you talk about real-time simulations, okay?
Yeah.
But there is a time in order to model your stuff, okay? Or the design part, I think that it's quite huge in the sense to understand how to model, I don't know, a ship, but whatever, no? You show us that basically it's a very versatile tool, right?
Yeah, sure.
So there is this first part about design, and another part that it's like, okay, there is a fire, how can I act, right? Can you please comment about a little bit about the time of designing stuff like that, and then the time of, you know, computational time in order to do a simulation?
Yeah, sure. There are a lot of times here, actually.
Yes, exactly.
You're totally right. There are a lot of times of time. Okay, yeah. Time length, let's say. So, I mean, regarding the designing part, designing that takes a lot, and I think, I mean, the more you spend, let's say, in some sense, the more you spend time on designing, then if you design it really well, then you should spend less time when you really need it. So, for example, I don't know, as I told you, our software is part of a pipeline. So what we're trying to do with Cefena, for example, is to get the best input. So the best way to get from their models to actually, I mean, useful models for our software. So to avoid all this designing part in that sense. Regarding the software itself, I mean, for now, as I told at some point, we are just playing with single plans. Single plans have, I would say, less than 100 nodes. So these are really the small ones, and it takes some seconds. So you get the results from some seconds. And especially, you know, the configuration of the switches, which is what ideally the main idea of this project, I didn't mention that, is to have a support tool. Now, support means that the people, the crew, should be able just to play with it. Now, it is still not defined if they will really play with it or if they will just have some cases and then our result in some cases. But ideally, for now, it takes some seconds. So it's really real-time thing. We should definitely check that on larger plans, because then we have, I mean, we have really an idea on how much. But we are still in the design phase, and we didn't arrive to that kind of on how large. But I mean, in any case, I would say that it is pretty real-time thing. I mean, of course, then probably what they said they're doing, they will probably store some scenarios and some results, you know, to have them, you know, to have what happens, not to have to query every time, even though it can be done, but that's more safe, because if you're in danger, also psychological aspects are not.
Yes.
Into account. About the time also, you need to react. That's another time. Yeah, that's what I would say.
Thank you, Martina. There is a question from Anna. So Anna, you can unmute yourself and ask a question if you want.
Thank you, and thank you, Martina, for a very great talk. Yeah, it's only like a follow-up of Maria's question. So, so you said that like right now you're playing with quite a small example, and if you go to, you know, like say more, I don't know, more realistic or larger example, will computational time will become an issue for you, a challenge, or it's still you think you will be within seconds and real-time simulation will be still easily obtained?
I hope not, but in any case, I think, no, I mean, I hope not. But in any case, I think it, in the end, what they're doing. But I mean, regarding that, I think also it's pretty much about how you can react. So it's really difficult to, I mean, you're in a ship with fire and you should play with a tablet with an algorithm. So how to say, you should be able to do that with this. Actually, we did some tests, as I was saying, regarding the parallelization with some thousands of nodes, and it went pretty well. So it didn't take hours, okay? Take still, I mean, seconds or maximum minutes, but I'm not saying like hours. But still, I mean, this is pretty, I mean, I don't know then India and if you're doing that, but no, I do not expect that to last hours. No.
I see. Yeah, because I really like your part with algorithms, and I was just curious. I mean, as soon as you have some problem with computational time, you may want also to try some stochastic methods, which would maybe be not so much accurate, but would give you results in a
that
small.
may be an idea. And also, I mean, what I think is the best, and that's what I'm really waiting forward to, is really playing with real plants. What I mean by that is that we've played a lot, especially in this Master in High Performance Computing thesis. So we did a lot of tests together with Nicola also about parallelization. But I mean, I would really like to see how are the real plants made. I mean, of course, here I didn't show any of them, but I would really like to play with some real ones. Or I don't know, for example, you may want to play with two plants together. I don't know, you may have, I don't know, one plant for power, one plant for water, I'm just saying, but they are together in one place. So the number of nodes just enlarges immediately. So you would like to be able to play with both of them. And whenever I get the answer, yeah, in the case that would be a thing. But the point is that I think still they want to, I mean, I know I said already that, but they want to stick with some, how to say, with some scenarios which are stored, because I think these are kind of the manuals for people. But in general, it's a good suggestion. Yeah, next time, I think so.
Thank you, Martina.
There's another question by Andrea.
Yeah, can you hear me? Ciao, Martina.
Yeah, ciao, Andrea.
Thanks for the talk. I have a question. You repeatedly said that we are now in the basically in the design phase or the development phase of the methodology, so of the digital twin itself. So one of the points of the digital twin, as you made it before, is that you have sensors on the physical object that will tell you how things are going. So could you think also, or have you thought also with the company about using optimization to provide you with information as to where to place the sensors, how many sensors are enough to get what the result you want, and things like that. In the sense that, of course, if the switch is, every node should have its own switch, a sensor for its own switch, but maybe fire sensors or things like that could be minimized somehow. I don't know.
We haven't. I mean, we haven't spoken about that, but that's really a nice idea. I mean, I really think that there could be a lot of room for improvement in this, because you know that on the ship you have a lot of sensors, and I mean, for now we are modeling that, and ideally, you know, the crew should make the thing. But I think that being more automatic would be really good, especially in this kind of framework. So yes, I think I've thought about that, even though I've not spoken and finalized now anything. But it would be very nice.
Okay, thanks.
Okay.
Also, because we're here, sorry.
Yeah, sure.
Don't worry, it's fine. Sorry.
No, they're all somehow related to the physical modeling. Of course, you want to go in a direction in which different systems, like, I don't know, interact with each other. So, for instance, like I would say that electricity influences the pumps of the water systems and so on. So have you already gave a thought? Did you get with the company to the point in which you sit and you try to model the interactions and how they look?
I've just done, okay, to be sincere, I have just done one example of that, and it was a case in which it was actually one of the cases in which the number of nodes increased immediately. So it's not just about interaction, it may be just about locality. So I mean that you may have the same plants just in the same place. So they may not interact, even though everything interacts. Okay, everything is connected, but they just may be in the same place and be fired at the same time. So that might be just a problem. We had the plant, and we had the generation of the power for the plant itself. and we could model one or the other. And I decided finally to model everything. I mean, I model both, but in a sense, we try to model everything to see, I mean, if the, how to say, if the problem arrives also at the generation level, what happens? So yeah, that's what communication I would like to have. Yeah.
I see.
So I mean, we are still on single plans, so it's pretty difficult for now. Having on the overall structures, I would really like to do this thing because I think it's fundamental. Because I don't think, I mean, if the fire happens to be in some place, then it can. And it's combined things. Yeah. Since we have also this parallel part, I think it's the best way to go. And okay, definitely regarding times and so on. But,
yeah, again, that is one effect, but I mean that's the physical location of a fire could be, of course, impairing every system in that compartment. But what I'm saying is maybe you lose the electricity because of a fire, and then all the pumps throughout. I mean, because the generator is located in one place, but somewhere else you don't have electricity and you cannot use the water or something like that. So I mean that's the interaction I see.
No, yeah, I see, and I think that's what I'm saying. I mean, for now, we have just seen single plants. So what I tried to do was ask if there were two plants in the same place. So, I mean, maybe the model, the schematic has different plants. And I said, okay, maybe I will model everything with one graph. The graph doesn't really care about if you are light or water. But my main aim is when we go to the overall structure, that would be the idea. So that's what service was built for. I mean, you can imagine of a single small plant, and then whenever that one gets broken, maybe in another area, totally disconnected, not disconnected, pardon me, that's the wrong word, totally far, you get problems. So my main idea is to use this service, maybe, I don't know, better development of it, better refinement, and to understand what are the consequences. So definitely, yes, that would be, I mean, that is just an embryo of idea, but that would be the idea, yeah.
Yes. Yeah, I'll ask you again about this over a coffee or something like that, because it's interesting.
Okay. Let's hope to have coffee very soon.
Yeah.
Yeah.
Thank you.
You're welcome.
Okay. Are there other questions for Martina? Okay, it seems to me that there are no questions. So I thank once again Martina for this talk. And with you guys, we see each other next Friday for the following AJS. Thank you.
Thank you. Thank you, guys.